And I want to hear it. So who did you agree with, Ben or Kelly?
Kelly.
Kelly.
Okay, I heard of Ben, I heard of Kelly. Sounds like we have a mix. So everyone who agreed with Kelly, gravity doesn't need an atmosphere or air. There's no air or atmosphere. There will still be gravity. So explain your reasoning. Go ahead, Lila.
Well, I just thought about like space and like the universe, and everything is like gravitationally attracted or affected in some way by everything else. So like the sun and the earth, like there's not air or an atmosphere between them, and yet they're still gravitationally like attracted to one another. And it's the same for all the planets, and all the planets also affect each other, not just the sun.
Nice. That's kind of nice large scale thinking. Anyone had any other reasoning or anything else they want to share for Kelly? All right, how about Ben? Gravity needs an atmosphere or air. If there's no air or atmosphere, there'll be no gravity. Explain your reasoning there. Anyone willing? Landon, I think you went with Ben, right?
Yes.
So what were you thinking?
I was thinking that there has to be some kind of resistance for there to be gravity. And there's just no push or pull when there's no air or atmosphere.
I like that thinking. Brings in more of the idea of forces. Anyone else go with Ben? All right, let's see how the vote came out here. It looks like, interesting. So most of you actually agree with Ben, and only about 41% of you went with Kelly. So, and the reasoning here, sort of similar to what you guys were sharing when we spoke. Gravity exists in space, right? That's kind of space. There's no atmosphere, no air. So this really has to do with our perception of it. Here on the surface of the Earth, where we live in an atmosphere, we see gravity like all the time, right? You all know that if you were to push something off your table, it would fall to the floor. If you were holding a pen and let go of it, it would fall to the ground. And then if you've seen movies and things like that, we all know that when an astronaut is outside of our atmosphere in space, like on the International Space Station, what happens when they hold a pen and let go of it?
It stays.
Yeah, just floats, right? So that kind of, I think, leads a lot of people to think, okay, there's gravity on the surface, right, where there's atmosphere, where there's forces and things that push, like Landon was saying, and there's no gravity out in space because clearly things are floating around. In reality, the more accurate answer is actually Kelly, in that there is gravity regardless of whether there's atmosphere present or not. And that's because you have to start thinking about gravity as not just such a strong force, like the kind of thing that makes everything fall to the ground, but it's something that exists between all objects, even in very, very tiny amounts. In fact, yeah, again, it's something we'll explore in a little bit. So this is cool to see. I'm curious to see, again, you might see a very similar question to this again on our next assessment. So keep in mind, again, that we'll kind of hopefully improve your understanding of this as we go forward. So, all right, our next task is just a really short do now reading quiz. This is number 2 on that tasks list. Go ahead and click on that. It should take you to a Google quiz that looks like this. There are 4 questions, and again, this is open notes, so feel free to refer to any digital notes that you took, or if you took notes on paper. I mean, I don't know if you have your notebook in front of you or not. I discourage you from doing that. It's much, the point is to have the skill of note taking to refer to and summarizing the information you're getting from the reading. So go ahead and tackle that. Again, I'll time us for about 3 minutes, and I'll keep an eye on how many responses we get. And I'm listening, so if you still have questions or anything, just let me know. 3 minutes, go. All right, looks like we have responses from everybody. So again, I'll have you unmute yourselves. How do we feel about that quiz?
Good.
All right. Did it work well on Canvas?
Yeah.
Cool. All right, let's take a look. I don't know what order you answered them in, but the first question I have is, why doesn't the moon fall to the Earth? Yes, the correct answer, which most of you got, is that the moon has high tangential velocity. What does that mean? Any ideas? What does it mean? Go ahead, Max.
So it's like a velocity that's parallel to the Earth's surface. I think that's what it is.
Yeah, so that's why, like, think about it how, like an apple falling to the ground, the apple is just moving straight down, right? And gravity's acting equally on the moon, but you're right, the moon is moving so fast at a sideways, like parallel to the surface of the Earth, that it never actually comes down to the Earth, right? You can think of it as sort of falling around the planet, which I know is a little weird to think, but that is literally how orbit works. This next question here, it's a really complicated definition of a mathematical equation. And it's the relationship between objects and how gravity, how we are attracted to each other via gravity. And the idea is that mass is directly proportional, that should have been the first blank, directly proportional to the product of the masses, and inversely proportional to the square of the distance between them. And so most of you got that. It is describing a mathematical equation in that you would put mass on the top of the fraction and distance on the bottom of the fraction. That's essentially what that complicated definition is saying, and we'll explore that a little bit later today. Next question was the inverse square law, which is the idea that the farther away, the more distant things are, the less gravitational force there is, right? So the farther away you are from something, the less you're going to be attracted to that thing. And that sort of explains why when astronauts go up into space, they're a long way away from Earth's center, they experience a lot less gravity. However, and I like this last question, if two objects are placed far apart enough, their attraction will eventually be zero. And it looks like most of you got that that is false. There is actually no such thing as zero gravity. I know we use that term a lot, like when astronauts are in space, they're experiencing zero gravity. It's not actually zero, it's very close to zero, right? It can get very, very low, but there's always gonna be gravity influencing you in some way, even in small, minute amounts. So pretty good, looks like you were feeling good from the reading, and we're gonna review and reinforce a lot of that stuff today. Before we move on, though, into our new unit, I want to wrap up the projects by looking at the vote. I do know that we didn't get to see Landon and Angela's videos, but that's something I will just watch, and I think I'm ready to go ahead and cast our vote now. It looks like we've got 11 responses, so there's one person who hasn't voted yet. So let me look at all of you right now. Be honest, how many of you have voted?
I haven't voted yet.
Oh, okay, so Tammy, if you click on, Tammy, if you click right on the Google form, I actually have it on that tasks list. It should actually take you right there. It's the third task right here. Let's check the voting form. So if you just click on that link, it'll take you to the voting form. You can cast your vote. Tammy, I haven't looked at the results, but if it's a tie, Tammy, you could be the deciding factor right now for the $100,000. Anyone can look at the task list. What is the reward going to be for the group that gets the most votes?
5 extra points.
Extra credit points for labs, +5, which I can add to an assignment if you want me to, but I'm thinking I'm just going to add it to the total overall. So, all right, it looks like we have all our votes in. Now I've got 13 votes. So maybe someone else who I wasn't counting as present voted, but that's good. It means we're only missing one person, actually. If anyone else hasn't voted. You did?
Voted for the wrong thing by accident. Like I clicked on the wrong thing, so
okay.
I want to change my vote.
I don't think so. I think I only allowed one. But let's just see the results. Okay, drum roll. Here we go. Wow. All righty. So you guys have like the widest distribution I have seen. So it looks like there were 2 votes for plastic pollution, 2 votes for oil spills, 1 vote for warming seas, 1 vote for ocean acidification, 2 votes for overfishing. But the clear winner was eutrophication with 5 votes. Tammy, was there something different you're going to vote for?
I was going to vote for plastic pollution.
Oh, okay. All right. Don't know if that would have made a difference. Looks like you would have been, yeah, it would have still been 3. So great. Who did eutrophication? Who are our 2 presenters for that?
Hello.
I don't remember.
Yeah.
Keone?
Me and Ben. Yeah.
Keone and, all right, nice. Congratulations. I will give both of you some extra credit points. And good job to everybody. I was impressed with the presentations and research you did and questions that you asked afterwards. I know we dragged this project out, but it was sort of nice to have this, I think, as a slower transition into this online learning stuff. And the environment will continue to be a theme throughout our lessons. So, great. All right. The next thing that we're going to do is I'm going to just quickly review some key points from the Hewitt reading using a PowerPoint. Just really quick, I'll go through like 4 slides. So if you want to take notes in your digital notebook, or if you want to just take notes on paper or just sit and listen, I am recording this, so you're welcome to do whatever you want. And then once I've reviewed that, we'll go through a few activities. I'll ask a few questions, and if you have questions of your own, just remember to unmute yourself and feel free to jump right on in and interrupt me. That is totally fine. So this is all based on the 4 sections that you read, and you can access these slides on your own as well. So again, as I was telling you guys before, I am also new to physics. This is not something I've taught before, and so it's kind of interesting reading through this chapter, watching a few videos related to it. And so why do I have a picture of an apple and a moon? What kind of famous historical story is this outlining?
Newton's.
Yes, so I knew this whole story about Newton and the apple, right? But I always thought that it was just that Newton was sitting under a tree and an apple hit him in the head, and he kind of came up with the idea of like, oh, like all things are pulled to the ground, and called it gravity and started to measure it. But in reality, that's actually not the point of the story. The story is that when he was hit in the head with the apple, he was also looking at what? What's that picture there next?
Moon.
Yeah, and he made a connection saying, well, you know, if the apple is pulled to the earth, the moon must also be being pulled to the earth. Here's our happy moon, with the same amount of gravitational force, right? So why isn't that falling on my head as well? And so that got him interested, and this was kind of a big breakthrough in the realm of physics and starting to think about how things are moving and attracted to the center of the earth. So kind of cool. I didn't know that detail about I think that's kind of widely misunderstood. But Newton made some major contributions to science, not only starting to explore the idea of gravity and how objects relate to each other. So, all right, let's get into the first little detail here. This is something we discussed a lot with the quiz, but just to kind of reinforce it. So why doesn't the moon fall to the earth? The reason is that it has a high tangential velocity, meaning it is moving in parallel to our planet. But you have to understand that there's sort of 2 things, and this is a lot of physics is going to be this kind of thing of looking at the idea of forces, right? So velocity is a movement that has a direction, right? So it is moving parallel to Earth's surface. You can kind of see there's a perfect match there. And there's also a gravitational force attracting it. And so that's what locks it in to the circular motion. And again, what do we call that when one object circles around another in space? Anyone know? Words right there.
Orbit.
Yeah, so that is orbit, right? The gravitational attraction along with the tangential velocity. I like this diagram because look over here. What would happen if Earth just disappeared?
It would just like keep going.
Yeah, so what's missing? What made the difference here? Why would the moon shoot off by tangential velocity? Like by taking away Earth, what did we remove?
Gravitational forces.
Yeah, right. You need that gravitational attraction to the Earth to get that sort of locked in circular velocity. And without that, then the moon would just continue to move with its own velocity, right? It would just keep going where it's going. In fact, a lot of planets, because they have gravity, planets can actually pick up things that orbit it. In fact, Earth, it's kind of interesting, and I didn't really know this, but we actually recently picked up another satellite. There was an asteroid that was passing by Earth that Earth kind of picked up, grabbed in its gravity, and so it rotated around the planet a couple times, and then it left again. And that's another interesting thing. So does anyone know there's something called orbital decay? And what that means is when you have a decaying orbit, what's happening to your orbit? Kind of drawing it here. What do you think we mean by decaying orbit?
It's getting smaller, like the orbited.
Yeah, you're getting closer and closer to the planet, right? This is a problem that a lot of our satellites have, right? That when we send a satellite into space, the satellites have to have energy and power, not only to get up there, but Earth is slowly pulling those satellites back down to its surface. And so they have to constantly readjust themselves to fix that distance. However, what do you think is happening to the moon? Do you think the moon is also going through orbital decay? Like, so eventually in, I don't know, like a couple million years, the moon is going to hit Earth? Or do you think the moon's actually getting further away from Earth and it's eventually going to escape our orbit? Any ideas?
I think it's getting further away.
That does seem to be the prevailing theory. I'm not entirely sure why, but that was what, when I looked this up, it is actually revealed the moon is actually getting further away. And so either the tangential velocity is just slightly high enough to remove it from Earth's gravity, or there might be other things at play, like maybe even the sun's gravity or something is playing a role here. But I don't know what implications that'll have on Earth. Does anyone know what pretty significant thing the moon contributes to on Earth? All this,
Tides.
yeah, all this blue stuff, tides and waves and things like that. A lot of ocean water movement is related to the presence of the moon. So again, I don't know if life, or at least life as it exists now, will be around then, but it'll be kind of interesting to see what happens if the moon does move away. Any questions or comments so far? Feeling good? All right, so the bad news is if we're going to move into physics, then we're going to start doing a lot of what? Math, yeah. We've had so much fun with math in the past. So yes, welcome to the world of equations again. This is an equation. F stands for gravitational force, and this is sort of one of Newton's kind of breakthroughs, is that this mathematical equation is simply relating m to d. What do you think m stands for? Like what's m1 and m2?
Mass.
Yes, it's the mass, right? It's how much space, or it's the amount of matter in two different objects, right? So we got to compare their masses. You multiply them. And then what do you think d is?
Distance.
Yes, it is the distance between the two objects that you are considering. And so to explain this weird definition that we saw in the quiz, by saying that mass is directly proportional, it just means that you're putting mass on top of the fraction, right? Mass goes up here because it is directly proportional to the force. In other words, the higher the mass of an object, what's going to be true about the gravitational force it exerts on the things around it, right? If you have bigger mass, is your gravitational force going to be bigger or smaller if it's directly proportional?
It's bigger.
Yes,
Bigger.
right? So bigger mass, bigger gravitational force. Distance is inversely proportional, right? In other words, that's why it goes on the bottom of the fraction, which means as distance between objects increases, what's going to happen to the gravitational force?
It decreases.
Decreases, yes. That's what we mean by inversely proportional, right? So the further away something is from something else, the less gravitational force there is. That's all there is to it, right? And understanding this equation, that's all you really need to grasp. There is another variable that is going to play a role here, and we're going to explore that. If anyone read ahead, we're going to put in a capital G here. It's called the gravitation constant, and it's just a really, really, really tiny number that sort of puts all this in context. Because right now, it would seem like, wow, like gravitational force is going to be a really big, number. Like it must be, like even me sitting in front of my computer, it would seem like I'm going to yank my computer towards myself just by the gravity of my body. In reality, that doesn't happen because of this constant, this G number, which it keeps everything really small. Kind of puts things in context is a good way to think about it. So talking about my body, my computer, there's not much gravitational force because the masses are so low, even though the distance is pretty close together. But think about the mass of planet Earth. Do you think planet Earth has a big mass or small mass compared to like a human?
Very large.
Extremely large, right? And so that's why we experience a lot of gravitational force relative to the ground below us, right? That's why objects fall towards it. That's why we fall towards it if we trip. It's because its mass is so big and the distance is pretty small. So it brings up the gravitational force value. And again, we'll explore a little bit more of that later on too, once we get into more math. All right, final thing is to explore that the inverse relationship that we were just sort of relating earlier. And that's what they call the inverse square law. Again, I know this all sounds really fancy, inverse square law, but the whole point is that, again, the farther apart objects are, the less gravitational pull there is. That's all you need to understand. When you hear inverse square law, just think about that, right? That the further away something is, the less gravity is present. What they mean by inverse square law is we can actually quantify, right, how much weaker is the gravitational force, and it's the square, you just divide by the square of the distance. That's the math behind it. So I like this diagram because it kind of simplifies it. I know this looks complicated, but it's kind of a nice simplification of this understanding. So here's our center of gravity, right? That's where our source of gravity is. It's the same thing here. Like think of it as the center of Earth. And if this is our distance of 1, so we're just kind of setting a context. I mean, this could be any number, but if you consider that just the distance, then this over here is twice the distance. Everyone with me so far? How we're twice as far away? So in terms of gravitational force, if this is setting the standard, right? So here's a gravitational force experienced at this set distance. If you're twice as far away, then how much weaker is the gravity? And again, if it's the inverse square, then we're just dividing by the distance squared. So think about it. If the distance is now twice as far, 2 times, right? We've gone from 1 to 2. Can anyone tell me what 2 squared is?
4.
4. So, and we're just doing the dividing by it. So in other words, the gravitational force is now 1/4 what it was earlier. What if we were 3 times as far away? What would the weakening of the gravitational force be?
1/9.
1/9. Where did the 9 come from?
Because you square 3.
Yep, right? If you're 3 times as far away, then you're taking the square of 3, and that's the value, right? It would be 1/9 of the value. So again, these could be any number, right? R could be 22 meters, and you would still be working with the exact thing, just taking the inverse square of it. So this is just kind of setting just a kind of nice simplified example. But again, I know this is kind of weird to think, like, what the heck's going on with this diagram? What's with all these squares, right? The squares are just kind of showing you the value, the distribution of it. But let's do an activity that I hope will kind of maybe put this in context a little bit more, and let's just play with our eyes a little bit more, because you can do the same thing with the idea of perspective. So I'm going to exit out of this because we're going to do this using the screen. Okay, so first thing I'd like you to do, let's all unmute yourselves so that you can ask me questions if you're not sure about what we're doing, and I can get feedback from you. We're going to play with our perspective, how our eyes see. First thing you're going to do is really simple. It just involves your hands. What I want you to do, and you can watch my screen here, you want to place one hand relatively close to your face and the other one about twice as far away, and keep them close together so that you can see both of your hands. So kind of like how I'm holding them, right? One hand closer, one hand further away. And then just try to look at both of them, get them both in your field of view. And again, if we're trying to demonstrate the inverse square law, then the hand that is furthest away from us should look smaller, right? And the hand that's in front of your face should look bigger. But when you're looking with both of your eyes, do you see like a really significant difference? I mean, is this hand really 1/4 the size? What do you think?
No.
It isn't, right? It looks a little smaller to me, but it's not 1/4 the size. And the problem is that we're looking with 2 eyes, right? Both of your eyes are kind of trying to compensate for this weird perception of size changing. So what you want to do is only look through one eye. And again, try to keep your hands close together. Like think about almost trying to cross your thumbs, but try that. Try looking with just one eye. And then you'll really notice like, oh my gosh, I got a little baby hand out there, right? I got a really big hand in front of me. Does everyone see how that really makes a difference now? And if you play with the distances a little bit, do you see how you could get the distant hand to be about 1/4 the size of the hand that's closer to you? Is everyone sort of getting that? When you look through just one of your eyes. So all you want to do is close one eye.
Yeah.
Anyway, that's just kind of a one demonstration of it. But it's a little unclear with our hands. So a better way to do it is to use something that has proportionate sizes to it. And it turns out that you can use dollar bills. So what I'd like everybody to do right now is take about a minute or two to see if you can go get 2 bills of money. I don't care what it is, if it's $1 bills or $5 bills or $20 bills, or if you really want to show off $100 bills, or Monopoly money or whatever else you might have. But please go take a moment and go find 2 bills that are of equal size. And this will work with euros and all that stuff too. So whatever you need, just get 2 things of equal size. Max, I'd probably work with pesos as well. And the reason we're using paper is because we want to fold it. So you need to be able to fold these a little bit as well. All right, here's what you're gonna do. First of all, with just one of the bills, I want you to fold it to make it shorter, right? So you kind of call that the, right, that's called a taco fold, I guess. So fold it like that, so it's folded in half. And then go ahead and fold it burrito style the other way. So you wanna make it like that. So again, one way and then the other way. In other words, you should notice, how have we changed the size? We've now made it what? Yeah, it is now 1/4 the size. So everybody there? All right, so now, what if I told you that there's a way that we can make both of these look the same size, even though this one is clearly 1/4 the size of this one. But there's a way we can get them both to look the same size, and that's by, again, playing with our perspective. So we're gonna do the same thing we did with our hands. Hold the folded one close to your face, and hold the unfolded one further away from your face, and there should be a point where you'll see, again, remember to look through one eye. So close one eye, only look through one eye, but you can get it to the point where they are the same size according to your vision. Everyone getting it?
Yeah.
There you go. So kind of cool to see that that's how perspective works, right? That the further away this is, if you hold this twice as far away from your face, it appears to be 1/4 of the size, right? It's equal to that. That's the inverse square law, right? That's what that's describing. But the inverse square law, in our conversation, we're applying it to gravity, and gravity works the same way. That if an object is twice as far away as another one, then it's experiencing 1/4 of the gravitational attraction that it normally would, right? So that's what, think of this demonstration when you think of the inverse square law again as well, is that, if we held something twice as far away from our face, it was 1/4 the size, and you did that with the bills. So great. All right, make sure you put your cash or money back in a safe place. We're done with those. I now want to move on to a longer activity, and I'm going to leave you to do it on your own, but I'll walk you through the initial instructions first. So here we go. I'm going to share my screen again. So we are now on task 5 on the list of tasks for class today. You're going to explore gravitational force with just 4 kind of simple activities, but I'm going to try to get you away from your computer. I posted a video of myself explaining and demonstrating the 4 things I want you to do. You're gonna need like a cup or a can or something that you can poke a hole in the bottom of. You'll need to be either outside or over a sink where you can have access to water, because you're gonna be dropping something with water in it. And then you'll need a piece of paper and some kind of heavy book. That's all you'll need. So watch the video and then go try to find the materials you need and do the same things that I demonstrate. There's 4 little activities that you need to do. Again, it's all explained in the video. The video is about a little more than 4 minutes long. And you can go do this on your own. You don't have to record yourself. I am trusting that you're doing these things. I just want you to observe what happens when you do these 4 different things. And there's questions I ask in the video, 4 questions. Once you've done these 4 little activities and made your observations, you're going to come back to the same task list, and on the very on the very bottom, you'll see I've got a Canvas discussion board called Exploring Gravitational Force. It'll look like this, and I just want you to hit reply and answer the same 4 questions that I ask in the video. It's basically you're making observations about the stuff that you did that I demonstrate in the video. So your task right now is to watch the video I posted. The link is right there. I'm using a service called Swivel that I use to film myself. But if that link doesn't work for some reason, I also posted it to YouTube. So that's the second link. In fact, it's embedded right there. So you could watch the video right in the post if you wanted to. But watch the video, do the same things that I do. Again, you don't have to film yourself. I'm trusting that you're gonna go try them. And then come back and work on the discussion. So We'll come back here into the main room when there's 10 minutes left in the period. So I want to come back at 9:30. So that gives you about 15 minutes to work on this. And I think that should be adequate time to at least do the 4 activities. Part of me thinks that, well, let's give you 20 minutes because I've been giving my other classes 20 minutes to get through this. So let's come back at 9:35. We'll still have 5 minutes left in the period, and that's enough time to wrap things up. So please come back to this main room at 9:35. So that's in 20 minutes. But otherwise, you can leave the Zoom room right now if you want, or just mute and hide your video, whatever you want. But just rejoin our Zoom classroom at 9:35, and I'll be here listening. So if you got a question or something doesn't work, just pop back in and check in with me. All right, go for it.
Thank you.
All right, can I have you all unmute yourselves for me, please? How was that?
Good.
Yeah?
Yeah.
What did a lot of you use? Did you end up using paper cups or cans or plastic bottles or something? What'd you use?
Paper cups.
Paper
Paper
cup.
cup. Paper cup.
All right, most of you have paper cups at home.
I used the Gatorade bottle.
Oh yeah. So who got splashed? Anyone get splashed when the water rocketed back up out of the sink or tub?
I'm glad I did it outside though, because I splashed the wall.
Yeah, that's what I guess maybe for April Fools I should have I should have edited that part out of the video where I warn you and just let everybody get stuffed. So I learned that the hard way the first time when I was trying it for the first time, and yeah, water went all over our kitchen. So, but it's another good demonstration of one of Newton's laws, that for every action there's an equal and opposite reaction. So when you drop a water container into a sink, the water shoots back up right at you. But did you hopefully all observe that it is pretty weird that when you drop both the cup and release your finger, that water does not dribble out of the bottom? Kind of cool thing. And again, it gets at this idea of Newton's idea of gravitational force, that gravity acts on all things the same way, right? And just like the moon is being pulled to Earth in the same way that an apple is, that is kind of a demonstration of that basic kind of simple thing. So, so this is how I'm hoping we'll keep labs going, is just kind of some little practical things that you can do at home, and might try to get more and more complex. And if there's stuff that you can't get or you're not able to do, then we'll maybe use breakout rooms or something, and you can work with someone who does have the equipment. We'll figure it out. So, Tammy, it sounds like you had a hard time getting the videos to work. I guess Tammy isn't quite with us yet, so I'll follow up with him. But all right. Again, you didn't have to have the discussion post done by now. If you do have it done, great. But if you don't worry. You can finish it as homework. One thing that's good to know about Canvas discussions is that you can post your answer, but then you can edit it later as well. And I like that feature. So don't feel like you have to answer all 4 questions. Like if you only have 2 answered, just go ahead and post it and then come back to the discussion, click on you'll see 3 little dots in the upper right corner of your window. And if you click on that, edit is one of the options, and you can just add text from there. Other homework for you. If you look, I've got it listed here on the tasks list, and there'll also be a separate sort of announcement post and a couple assignments that should pop up once class is over. But if you have not completed your discussion post, please do so. I would like you to answer some questions from Hewitt chapter 5. If you look at the end of chapter 5 in Hewitt, it's on page 116. There are what are called reading check questions. Here's a digital version of Hewitt, so this is what it'll look like. And on page 116, you'll see reading check questions, and I want you to answer the odd questions up to 7. So 1, 3, 5, and 7. Please answer those in your Google Doc digital notebook. Question 1 is about Newton and his apple and his moon thing. Question 3 is about the moon falling. 5 is about the relationship between mass and gravity. And 7 is about the distance inverse square law stuff. Or actually it's a trick question about it being 0. So please answer those again in your digital notebook. And the way that you're going to submit that is you should see an assignment on Canvas that's literally just called Hewitt chapter 5 reading check questions 1, 3, 5, and 7. I want you to go ahead and click Submit Assignment, and then it'll ask for a website URL. And please just paste in the share URL to your digital notebook. So on your digital notebook where you answer the questions, just hit share and copy that URL in there. And that way in SpeedGrader, I can just go straight to your notebook. I'll find your answers wherever they are amongst your notes, and then I'll grade them from there. Questions on that at all? All right. The only other piece of homework, if you have not done so already, there is a feedback form. It's just 3 questions about how things are going so far in the class, basically how you think we're doing in Science 2, overall, anything your other teachers are doing that you'd like to see me do, and just how you're feeling about the amount of screen time that you've been experiencing with this online learning. So we got about 9 responses, so there's about 4 or 5 of you who still need to do that. But that is it for me. So as usual, I will linger here in the classroom if you have questions or individual concerns, but otherwise, thank you very much. Have a good day.
Thank you, Mr. Haight.
Thanks, Mr. Reed.
Thank you.
Thank
See
you.
ya.